Many of us have grown up with the idea that Earth simply revolves around the Sun, which stays still in space. But in reality, the big picture is much more complicated and fascinating. As we delve deeper into how Earth actually moves through the galaxy, we'll find that our planet not only revolves around the Sun, but is dashing through space at an incredible speed at the same time, along with our entire solar system. But what if we told you that this movement could be connected to some of the universe's greatest mysteries? For instance, scientific hypothesis suggests that Earth's movement through the galaxy may expose us to cosmic rays, which would cause genetic mutations and contribute to the mass extinction of life. Furthermore, changes in our planet's orbit around the Sun may affect the environment, which could lead to catastrophic changes, such as another ice age. Understanding how our planet moves through the universe, we can appreciate our place in space more. We may even find clues to answer some of the bigger questions, such as how our galaxy formed and what the future holds for us. For starters, imagine that you're in an airplane that's flying at a constant speed and altitude. While in it, you won't be able to tell how fast you're going or even if you're moving at all. From your point of view, it seems that only the world outside is moving. However, someone on the ground watching a passing aircraft will perceive its movement relative to their own stationary position. This outline, which was first outlined by Galileo Galilei in his 1632 book, The Dialogue Concerning the Two Chief World Systems, to express what we now call Galilean relativity or Galilean invariance. It's the concept that defines the absence of an absolute frame of reference for motion. And even when there are several valid frames of reference, we still need to choose the most relevant one, depending on the situation. So how does this fit in with the idea of Earth's movement and the solar system as a whole? First, we need to determine the observation point. When viewed from within our star system, as we all know, the planets orbit the Sun. However, with a broader consideration of things, we can see a completely different picture. The solar system is constantly moving in a spiral through the expanse of our galaxy. One of the best known examples of relative motion within our solar system is Earth's revolution around the Sun. Earth's orbit is not a perfect circle, but rather an ellipse with the Sun as one of its foci. That means that at some points in its orbit, Earth is closer to the Sun than at others. When Earth is closest to the Sun, it is said to be at perihelion, and that the farthest point in its orbit in relation to the Sun is known as aphelion. These 2 points occur at regular intervals. Earth reaches perihelion around January 3rd and aphelion around July 4th, which is evident with the seasonal changes of the weather. You know the usual depiction of the solar system, with the Sun in the center and the planets revolving around it. Well, that's not a completely accurate representation of the movement within our planetary system. You see, the planets don't just revolve around the Sun, but they also pull it in, causing it to shift. For example, the gas giants Jupiter and Saturn have a particularly strong gravitational influence on the Sun and Earth, which causes small changes in the shape and orientation of their orbits. When Jupiter and Saturn are even remotely lined up, they have a significant effect on all the bodies in the solar system. This effect is known as the perturbation of the outer planets. Over time, these subtle changes in Earth's orbit can accumulate, leading to long-term changes in the planet's climate and overall environment. These changes are known as Milankovitch cycles. One of the aspects of the Milankovitch cycles is the change in the tilt of the Earth's axis, which shifts from about 22 to 24.5 degrees in a cycle of about 41,000 years. This change in the planet's tilt affects the amount of solar radiation reaching different parts of the Earth's surface, which in turn can affect the timing and intensity of glaciation periods, ice ages. Based on these cycles, some scientists predict that in the relatively near future, a new ice age may begin on Earth, spanning across tens of thousands of years. However, it's important to note that the effects of an anthropogenic climate change are currently suppressing Earth's natural climate cycles, making it difficult to predict the exact timing and intensity of future ice ages. Let's face it, Earth's movement pattern within the solar system is very complex. However, its movement through the galaxy is even more intricate. The Milky Way galaxy is a massive and complex system which includes a vast amount of stars, gas, and dust spanning across over 100,000 light-years in diameter. One of the most exciting aspects of our galaxy is its rotation. Like a huge spinning windmill, the galaxy's spiral arms trail along as it spins. This rotation makes the stars and gas in the galaxy move in circular orbits around the galactic center. Earth is located in one of the spiral arms of the galaxy, about 25,000 light-years from its center. In the solar system, there are only a few bodies that have to be taken into account in terms of gravity, and the Sun is the dominant celestial body in this gravitational field. In contrast, the Milky Way's gravitational field has no dominant object. Instead, everything revolves within the total gravitational fields of everything else. This makes tracking the motion of the galaxy's components a difficult but rewarding task, allowing us to learn a wealth of information about the complex structure of our galaxy. Just as Earth orbits the Sun revolves around the center of the Milky Way galaxy at a speed of about 143 miles per second, completing one orbit in almost 230 million years. This cosmic journey takes the Sun, and therefore also Earth, through different regions of the galaxy and introduces us to different cosmic environments. Interestingly, the stars in the inner regions of the galaxy move faster than the stars in the outer regions due to the fact that the parts closer to the center of the galaxy have more mass and therefore a stronger gravitational pull. This difference in speed is akin to the way planets closer to the Sun move faster along their orbits than those farther away. Determining the speed of the Sun relative to the center of the galaxy involves searching for new, young stars that have only recently formed and are therefore still in their birth orbit. Next, taking an average of how these stars move relative to us, we can deduct that the Sun is drifting forward at the speed of about 3.1 miles per second, in towards the galactic center at a speed of about 5 miles per second, and up and out of the galactic disk at about 4.4 miles per second. This small, peculiar motion has huge implications for the path that the Sun and solar system take through the galaxy. The orbit of the Sun around the center of the galaxy is not perfectly circular either. Instead, it follows a slightly elliptical path, oscillating above and below the galactic plane. It completes a full oscillation approximately once every 60 million years. This movement is influenced by the gravitational pull of other stars, gas clouds, and dark matter in the galaxy. We're currently several dozen light years above the middle plane of the galactic disk, although it's difficult to determine exactly where the center is. Since there is more matter below us than above us, the gravity of the disk slows the upward movement and, in a few million years, will be about 300 light years above the center of the disk before our upward movement slows to a complete halt and we begin to descend. The vertical oscillation is more than just a peculiar phenomenon. Some astronomers support the Shiva hypothesis and believe that it can be directly related to mass extinctions on Earth. since the center of the disk is a more dangerous place for the solar system due to the higher density of stars and the radiation they emit. The motion of the galaxy's spiral arms is not yet fully studied, but is theorized to be caused by a combination of factors. One of them is the gravity of other galaxies in the local group, the cluster of galaxies that includes the Milky Way. Another factor is the existence of density waves, which are believed to propagate across the galactic disk like ripples in a pond. These waves can force stars and gas in and out of the spiral arms, potentially affecting the environment and living conditions on Earth as we pass through these regions. For example, as the Earth passes through an area of higher density, there may be more cosmic rays and other high-energy particles reaching the surface of our planet. This could have implications for our climate, atmospheric chemistry, and even the evolution of life on Earth. As we discussed previously, the Sun is not stationary. It moves through the Milky Way galaxy, dragging Earth and the other planets along with it. However, the Sun is not the only moving object. All other stars in the galaxy are also in motion. The motion of the stars can be defined in terms of their proper motion, which refers to the star's visible motion across the sky over time. Proper motion is caused by the movement of stars in space relative to the Sun. It's usually measured in arcseconds per year, which is the angular displacement of a star in the sky over the course of a year. The concept of proper motion allows astronomers to track movement of stars over time and study their movement and position relative to each other. This is important because it helps us get a better grasp of the structure and dynamics of the Milky Way. Now, let's take a look at the movement of Earth relative to the nearest stars. Due to Earth's movement around the Sun, the apparent positions of nearby stars in the night sky change slightly over time. This effect is known as parallax. It happens due to the fact that at different times of the year, Earth is in a different position in its orbit, resulting in slightly different viewpoints for nearby stars. The amount of parallax observed for each particular star depends on its distance from Earth. Stars that are closer to Earth will display more parallax than those that are farther away. Astronomers can use the amount of observed parallax to determine the distance to nearby stars, which is an important tool for understanding the size and structure of a galaxy. In addition to parallax, our perception of the night sky is also affected by the proper motion of nearby stars. Over several years or decades, the position of nearby stars can change markedly due to their own movement in space. This means that the constellation patterns we see today will look somewhat different in the future and would have looked somewhat different in the past. The effect of proper motion is especially noticeable for nearby stars that have a large proper motion, or in other words, the fast-moving stars. Now that we have a breathtaking picture of the way our solar system actually moves through the galaxy, one question remains. How do we move through the universe as a whole? As it turns out, the Milky Way is not alone in its travels. Our galaxy is constantly pulled by the gravitational fields of various masses surrounding it. We're currently racing towards the Andromeda Galaxy at the speed of a couple of hundred miles per second. But that's not all. The Milky Way is part of a group of galaxies called the Local Group, which includes more than 54 other galaxies, including our nearest neighbor, the Andromeda Galaxy. The Local Group, along with many other groups and clusters of galaxy, is moving towards a mysterious superdensity in a supercluster of galaxies known as the Great Attractor. The Great Attractor is a region of space about 150 million light-years away, and its gravitational attraction is so strong that it influences the motion of galaxies within hundreds of millions of light-years. As a result, the Local Group is pulled towards the Great Attractor at a speed of about 373 miles per second. However, this movement is still not the last of Earth's movement in the universe. Our entire universe is expanding, and as a result, all the galaxies in it are moving away from each other. This expansion is not a movement in space, but rather a stretching of space itself. The universe is expanding at an accelerating rate, and as a result, the distance between galaxies increases over time. Despite all of this motion, we can still use the cosmic microwave background radiation as a frame of reference for determining our speed relative to the rest of the universe. This radiation, which is the residual heat of the Big Bang, permeates the entire universe and is almost uniform in all directions. By measuring tiny variations in this radiation, scientists have determined that Earth and our entire solar system are moving through the universe at about 229 miles per second relative to the cosmic microwave background radiation. At this point, it's no longer a stunning revelation to anyone that Earth is far from stationary, but rather a tiny but important part of a complex system of celestial movements. The pronounced complexity of the motion of our planet is an impressively complex phenomenon. First, our planet gracefully orbits the radiant sun as it has for billions of years. But that's just the tip of the iceberg. The solar system, which our planet is a part of, also moves through the vast expanses of the Milky Way galaxy, rushing forward at incredible speed and leaving a corkscrew pattern behind it. And that's still not all. The Milky Way is part of a galactic congregation known as the Local Group, which includes a number of nearby galaxies. And together, they perform this cosmic dance as they move toward the mysterious gravitational force known as the Great Attractor. And this tug-of-war causes the Local Group to dash through space at several hundred miles per second. But even that is not the end of the story. The universe itself is expanding, a fact that has been known since Edwin Hubble's groundbreaking discovery in the 1920s. This expansion means the galaxies are moving away from each other at an astonishing rate. In conclusion, Earth is not just a rock flying through space. It's part of a grand scheme, a web of cosmic movements, both intricate and awe-inspiring. We're just a tiny speck of dust in the vastness of this universe. But the movement of our planet is an integral part of the puzzle that is space.